Today we're going to be talking about the purpose of IP addressing, and then we're going to move on to some IPv4 address properties. There's a whole lot of ground to cover and we need to do it quickly, so let's go ahead and begin this session. Of course, we're going to start with the purpose of IP addressing. When Bob on network A wants to view a web page hosted on a server on network C, how does Bob's computer know where to send him? Well, somehow Bob has gotten that server's IP address, either in IPv4 format or IPv6. IP addresses are the location of a PC or server or some other network device that identifies it by both its network location and host location within that network. IP addressing provides a logical addressing scheme for our computers so that they can communicate on networks. Being logical means that the IP address can be changed with minimal fuss at any time, unlike the MAC address or the Media Access Control address, which is physically embedded into the device. On the other hand, IP addresses are programmed in and are easily changed. Now that we know the purpose of IP addressing, let's move on to some IPv4 address properties. IPv4 is made up of a 32-bit binary number. That means there are 2 to the 32nd power possible address combinations. That gives us 4,294,967,296 possible address combinations. With all of these possibilities, a process needed to be developed to keep everything neat and tidy, and, most of all, findable. The implementation of a subnet mask was the answer, and I'll get to that subnet mask in just a moment. Something that you will find useful is learning how to convert from binary to decimal. Now, decimal is base 2. That means there are only zeros and ones, as opposed to the base 10 that we're all used to dealing with. If you would like more information on how to convert from decimal to binary or binary to decimal, you can go to that website that's listed under this heading. So now let's talk about the initial properties of IPv4. It is a 32-bit binary number, as I said before. It's divided into 4 sets of 8, called octets. These are separated by periods, or decimals. Each octet is 8 bits, which equals 1 byte. We often represent IPv4 addresses in a human-friendly format that's called dotted decimal. Now, when we look at this address, 192.168.1.9, that is an IP address, but we don't know which portion is the network or which portion is the host. To be able to resolve this, it requires the use of a mask which determines or defines which portion is which. This mask is called the subnet mask, and the subnet mask has the same format as the IP address, as in it's 32 bits and it's represented in dotted decimal format. So let's take a look at how an IP address and subnet mask operate together. So we're going to begin with 192.168.1.9 with a subnet mask at 255.255.255.0. Now the 192.168.1.9 is the IP address, like I said, and the other portion, the 255.255.255.0, is the subnet mask. And it's easiest to show how the subnet masks by converting that dotted decimal back into binary. So we can do that by deconstructing the IP address. So the first octet would be 11 followed by 6 zeros. That equals 192. The second octet is 10101 followed by 3 zeros. That equals 168. That third octet's real easy. It's 7 zeros followed by a 1. And then we have the fourth octet, which is 4 zeros, a 1, 2 zeros, and a 1. That equals 9. Now if we deconstruct the subnet mask, what we have is we have 3 octets that are full of ones and 1 octet that's full of zeros. That represents that 255.255.255.0. Now, if we put the subnet mask under the representation of the IP address, anything that's not covered by a 1 in the subnet mask is a part of the host address. Everything that is covered by a 1 is the network address. So what we have for that IP address is that 192.168.1 is the network portion of the address, and the node portion of the address is the 9. And that's how the IP address and subnet mask work together to define the network and the node. Now that concludes this session on the Introduction to IPv4, Part 1. We talked about the purpose of IP addressing. And then we moved on to some IPv4 address properties, classes of IPv4 addresses, and then we're going to move on to classless IPv4 addressing, and we will conclude with a brief discussion on subnetting IPv4 addresses. There's a whole lot of technical information to cover, so let's go ahead and begin this session. Let's begin by talking about classes of IPv4 addresses. Internet Protocol Version 4, IPv4, is a binary addressing scheme that's used for networking. It was initially finalized as a standard in 1981. IPv4 is a common network addressing scheme that is still being deployed today. There is an issue, though, with IPv4. Because of its structure and the growth and popularity of the internet, most of the world has run out of assignable IPv4 addresses. But thanks to some forethought, it's still a valid scheme today. We need to talk about classes of IPv4 addresses, and we begin with a Class A network address. Class A networks have an address range of 0 to 127 in the first octet. That gives us addresses from 0.0.0.0 up to 127.255.255.255. The first octet on the left has a binary representation that always begins with a 0. This gives us a possible 16,777,214 host addresses. And the subnet mask with a Class A network is always 255.0.0.0. Then there are Class B network addresses. They have an address range of 128 to 191 in the first octet. That means that Class B networks can have a range of 128.0.0.0 up to 191.255.255.255. The first octet on the left always has a binary representation that begins with a 10. Now, Class B network addresses give us a possible 65,534 hosts. And the subnet mask used with a Class B network is always 255.255.0.0. Then there are Class C network addresses, and they have an address range in the first octet of 192 up to 223. That means that we have an address range of 192.0.0.0 up through 223.255.255.255. And that first octet on the left always begins with a 110. Class C network addresses give us a possible 254 host addresses or node addresses. And the subnet mask with a Class C is always 255.255.255.0. The last class of address that you need to concern yourself with is the Class D network address. It has an address range of 224 up through 239 in the first octet, which means that it can range from 224.0.0.0 up through 239.255.255.255, and that first octet on the left has a binary representation of 1110. So the first 4 bits are always taken, and they are always 1110. Now, subnet masks are not defined for Class D networking. Class D network addresses are used for multicast communication. And finally, we have a special class of addresses. Well, kind of a class of addresses. And that involves automatic private IP addressing, a PIPA. In some cases, the Dynamic Host Configuration Protocol, DHCP, process may fail. In these cases, a node or host will self-configure an APIPA address. Now, with an APIPA address, the first 2 octets are always 168.254. And if you see that in your IP configuration, you know that you have a DHCP problem. So one of the first methods that they used to conserve the IPv4 address space was they broke them out into public and private IP addresses. Public IP addresses are routable. And being routable means that each public IP address is unique. There can only be one. Now, public IP addresses are not flexible. You are assigned to your network space. You're not really given a choice what your public IP address is going to be. And then there are the private IP addresses. These are non-routable. They do not need to be completely unique throughout the world. They only have to be unique on their network. The first one that we're going to discuss is the Class A license. There is only one Class A license. You have a possible address range of 10.0.0.0 up through 10.255.255.255. Next up is the Class B license. There are 16 possible network addresses, not network and host, but just network addresses available in a Class B license. They have an address range of 172.16.0.0 up through 172.31.255.255. And last but not least is the Class C license. There are 256 Class C licenses, with a possible address range of 192.168.0.0 up through 192.168.255.255. Now, private IP addressing is highly flexible. You get to assign the network space. It's not assigned to you. Now let's move on to classless IPv4 addressing. Now, the classes of addresses actually limited the flexibility of IPv4. Part of the reason for that was that the first routing protocols required the class structure. And you would think that with over 4 billion possible IP addresses that we'd still have flexibility, but we really didn't. Classless addressing, which is called Classless Interdomain Routing, or CIDR, was developed to slow the growth of routing tables. It also slowed the exhaustion of IPv4 addresses. It also created much more flexibility. The subnet mask becomes fluid. It's not rigid with CIDR addressing. It does not affect the private address space ranges, though. Even though the subnet mask is now fluid, you still only have those range of addresses available. And with the introduction of classless addressing, subnetting is now possible and it's highly desirable. So let's take a look at how CIDR notation works. And we'll begin with 192.168.0.9 with a subnet mask of 255.255.0. What that becomes is 192.168.0.9/24. That /24 represents all of the ones in the subnet mask. And that's those first 3 octets on the left, the 255.255.255. And if you look at that address, it's a Class C address, which always has a 255.255.255.0 subnet mask, but it now becomes fluid with CIDR. We can take it and we can make it a 192.168.128.0/23. And what that really represents, that /23, is a subnet mask of 255.255.128.0. And that gives us a network of 192.168.128.0, which actually gives us a host range of 192.168.128.1 through 192.168.129.254. That gives us 512 host addresses as opposed to the possible 254. Now the broadcast address for that network would be 192.168.129.255. So now let's move on to subnetting IPv4 addresses. So what is subnetting? Well, subnetting cuts address spaces into smaller pieces. It takes one range of addresses and splits it. This creates flexibility in network design and creates efficiency in address space utilization. So let's take a look at an example of subnetting. And this will involve a small office network. So originally, we have a network address of 223.15.1.0/24. This is a Class C private network, and it gives us a possible 254 hosts available. Why only 254? Well, because a host cannot be assigned the network address, which is 223.15.1.0, and it can't use the broadcast address, which is 223.15.1.255. In this example, with this network address, all the hosts in the network can see all the other nodes. Now let's say that for security considerations, you want to split this into two networks. Well, you can do this using subnetting. So what you do is you take that /24 network and you create two /25 networks. And those would be 223.15.1.0/25 and 223.15.1.128/25. In this situation, the first network's host address range would be 223.15.1.1 up through 223.15.1.126. And why is that? Well, because you can't use the network address, which is 223.15.1.0, and you can't use the broadcast address, which is 223.15.1.127. The second address range that would be created through this subnetting process would give us a host range of 223.15.1.129 up through 223.15.1.254. That's because you can't use the network address, which is 223.15.1.128, and you can't use the broadcast address, which is 223.15.1.255. Each of those subnets would have 126 possible host addresses. So you took your possible 254 hosts available in one network and you broke it down so that you now have two separate networks, each that's capable of having 126 hosts. And that's an example of subnetting an IPv4 address. Now that concludes this session on the introduction to IPv4 Part 2. I talked about classes of IPv4 addresses. I then moved on to classless IPv4 addressing, and we concluded with a brief discussion on subnetting IPv4 addresses.